Alright everyone, so with these next two videos we're going to wrap up the entire course. So these next two videos I'm going to do are going to be an introduction to things you'll see in Calc 2. The first thing that you'll notice is that this is going to be a little bit different because I'm doing this outside today, mostly because I'm kind of sick of being inside. So I'm doing these down at the western shores of Lake Ontario. So if you can see a very kind of tall spire far in the background over to my right, that is Toronto's CN Tower. So, okay, so what we want to do in this first video is we want to talk about undoing the chain rule. So much of what we spend our time on with derivatives has been undoing, or we spend our time with derivatives doing product rules and chain rules. This first video I'm going to talk about how we undo the chain rule. Second one I'm going to talk about how we undo the product rule. And this is a main focus of the things you have to do in Calc 2, so this, it's a worthwhile introduction to have. Okay, so before we do that, let's just recap what we did with the chain rule. So remember that we'd said that if we have some function composition f of g of x, that derivative is f prime evaluated at g times g prime. So what we could do is we could take antiderivatives of both sides. Our antiderivative on the left will just be f of g of x, and on the right-hand side we'll get an antiderivative for f prime of g of x times g prime of x dx. Now, to find this antiderivative, what we're going to do is we're going to make a quick substitution. We're going to change variables from looking at things in terms of x to looking at things in terms of u, where u is going to be g of x. And when we do that, we then need to find the derivative of u. So du by dx will just be g prime of x. And what we can do is we can treat the expression on the left as just fractions. So we can treat it as some quantity du divided by some other quantity dx, and we can solve for the dx. Doing that, we get du over g prime times dx. Okay, so then we want to insert that expression that we have for dx back into the thing we started with. So what we'll see is that we have a g prime in the numerator and a g prime in the denominator. And when we cancel those two things off and then insert u for g of x, we get an antiderivative of f prime of u du. And then finding the antiderivative of that is just f of u plus some arbitrary constant. Lastly, we have to put things back in terms of x, so we finish off with f of g of x plus c, which is exactly what we want. Okay, and the main takeaway from this is that whenever you're going to do a substitution, you want to make sure that the derivative of whatever you substitute in is sitting in your numerator up to a constant multiple. So if we had some extra constant multiplied by the g, not a problem, because that's easy to take care of. Okay, so we'll go and walk through a few examples. So I have 7 examples for these. Okay, so the first one that we're going to do is going to be find the integral of x over x squared plus 1 dx. Okay, so for this what we can do is first we can say, well, if we take u to be our denominator of x squared plus 1, we'll get a derivative of 2x. So we have a multiple of the thing that we're going to substitute in, its derivative, sitting in the numerator. So when we do that, we'll take du is going to be 2x dx, or dx is du over 2x. So now we're going to go and substitute things into our integrals. So we're going to have the integral first of x over x squared plus 1 times dx. We can substitute in the u for x squared plus 1, and then substitute in du over 2x for dx. And when we do that, we see that that x that was sitting in the numerator is going to cancel with the x sitting in the denominator. And then we'll get the 1/2 out in front. So we get 1/2 times the integral of 1 over u du. We know how to do the integral of 1 over u du. That's just natural logarithm of absolute value of u plus c. And then the last step that we need to do is substitute back in the expression u equals x squared plus 1. And when we do that, we get the final answer is 1/2 natural logarithm of the absolute value of x squared plus 1 plus some arbitrary constant. Now, the other nice thing about finding antiderivatives is that you can always check your work. So if you wanted to go back and verify that you have actually found the antiderivative for the thing you started with, just take the derivative of whatever you get in your answer. And if you don't get back what you started with, you've done something wrong. Okay, so for our second example, we want to find an integral or an antiderivative for tangent of x. So we know how to find derivatives for tangent of x, secant squared. We can find an antiderivative for secant squared. That'll just be tangent plus some constant. But let's go and find an antiderivative for tangent. Okay, so typically whenever you're doing things with trig functions, you want to put things in terms of sines and cosines because it just makes things easier to work with. So we'll do that first. We'll go and rewrite tangent as sine divided by cosine. Again, what we want to do is we want to go and make a substitution so that the derivative of what we substitute in is sitting in our numerator. So if, for example, here we could pick u equals sine or u equals cosine, if we pick u equals sine, we would get a derivative of cosine, which wouldn't actually be sitting in our numerator. So we'll pick u to be cosine, and then when we get the derivative of minus sine, we see, yes, there is a constant multiple of sine, of minus sine, sitting in our numerator. Okay, so then we can rewrite dx as minus du over sine of x, and then we'll just substitute in the various things that we've put here. So we'll have sine of x divided by u, where u is cosine, and then that'll be multiplied by our minus du over sine of x, and when we make this substitution, we then get minus the integral of 1 over u du. Again, we'll get minus natural logarithm of absolute value of u plus some arbitrary constant c. And then lastly, we'll go and substitute in our expression u equals cosine of x. So what this says is that an antiderivative for tangent of x is minus the natural logarithm of absolute value of cosine plus c. Okay, so far, this should be pretty straightforward. The main idea is, as I've been saying, just substitute in a constant. You want to make a substitution so that a constant multiple of whatever you substituted in, constant multiple of the derivative of whatever you substituted in, is a factor of the numerator. Okay, so the next one we want to do is sine of 3 natural logarithm of x. Okay, so if we do this, there's maybe not an obvious thing to do initially, but what I'm going to propose is that we use u equal 3 natural logarithm of x. So that way when we do that, we get our du is going to be equal to 3 over x dx, and the 1 over x, so we can think about it as we have an x sitting in the denominator of what we started with. That's the same thing as saying that we have 1 over x in the numerator. So we have 3 over x, which is a constant multiple of something sitting in the numerator. So after solving for dx, we get that dx is going to be x over 3 du, and then we're just going to substitute in our various pieces. So we have sine of 3 natural logarithm of x divided by x dx. Well, we said that 3 natural logarithm of x is u, and then dx is x over 3 du. So we'll get the x that's in the denominator, we'll cancel with the x that we're going to bring in from the substitution, and we'll just reduce this down to finding 1/3 the integral of sine of u du. Remember that the antiderivative of sine is minus cosine, so we'll get minus 1/3 cosine of u plus some arbitrary constant c. And then sticking back the original expression we had for u, we get minus 1/3 cosine of 3 natural logarithm of x plus c. Okay, so then we want to move on and find the antiderivative of e to the x times the square root of 1 plus e to the x dx. Okay, so again here we want to go and make a substitution that will help us the most. So one thing we could have done is we could take u to be e to the x, and if we do that, then we would have a constant multiple of that derivative sitting in the numerator, just e to the x. But what we can do is we can also embed that plus 1 that's sitting under the square root inside of our substitution to make things easier on ourselves. So when we do that, we take u to be 1 plus e to the x. We still get that du is going to be e to the x dx. So we have a constant multiple of our derivative sitting in the numerator of our expression. Okay, so then we can write dx as e to the minus x du, and then just put in our substitutions. So we'll have the antiderivative of e to the x times the square root of 1 plus e to the x dx. We can rewrite it as an antiderivative of e to the x square root of u times e to the minus x du. the e to the x and the e to the minus x will cancel each other out. We'll just be left with square root of u du. Okay, so then from our power rule, we'll get that our antiderivative for this expression will be 2/3 u to the 3/2 plus an arbitrary constant c, and then we'll go and reinsert our expression u equals 1 plus e to the x. So we wind up with a final answer of 2/3 times 1 plus e to the x. That's raised to the 3/2 plus our arbitrary constant c. Okay, so in our fifth example, so we're going to have 1 over x squared plus 4x plus 5. Okay, so one of the things that we've done when we were particularly doing limits was we used the multiply by 1 trick to go and simplify things out. So we would have, so typically when we were multiplying by conjugate, we'd have something like find the limit as x goes to 3 of x minus, I don't know, square root of x minus square root of 3, and then we'd have like an x squared minus 9 in the denominator, something like that. And we'd use a constant multiple trick, or we'd use the conjugate. Anytime we were using the conjugate, we'd be multiplying by 1. What you tend to do with integrals is you add 0 in kind of clever ways. So that's what we're going to do here. Just because off the top, there's nothing really obvious to do. So the only real function of x that we have sitting here is this x squared plus 4x plus 5. If you use that as the u, you'd get 2x plus 4, which is not sitting in our numerator. So we're going to add 0. We're going to add things kind of cleverly. Okay, so the first thing we're going to do is we're going to write 5 as 4 plus 1. Okay, so that's great. And then what I'm going to do is I'm going to put parentheses around my x squared plus 4x plus 4, because that is a perfect squared trinomial. So what we can do is we can rewrite that denominator, instead of x squared plus 4x plus 5, as x plus 2, and that quantity is squared, and then plus 1. Now, doing that, I'm then going to choose u to be x plus 2. And what's nice about that is then du is dx. So when we do that, we get the antiderivative of 1 over 1 plus u squared du, and you may or may not remember that that is the derivative for arctangent of u, which I've conveniently had sitting down at the bottom of this page for a few times. So when you see something kind of suggestive like this, it says that maybe at some point you're going to need to use this. Okay, so nice and simply, we're just going to substitute back in at the end u equals x plus 2, and our derivative then is arctangent of x plus 2 plus some arbitrary constant c. So I've also had the derivative of arcsine sitting at the bottom of the page the entire time. So after we saw that we just used the derivative of arctan in the last one, we'd figure that we're probably going to use the derivative of arcsine in one of these two remaining ones, and given that the sixth one kind of looks closer to the derivative of arcsine than the seventh one, we'll see that we use the derivative of arcsine here. Okay, so we'll do the same kind of trick. We'll first start by factoring some things and then see that our integral is kind of nice and easy. So what we have is 1 over the square root of e to the 2x minus 1 dx. The first thing we can do is factor an e to the 2x out from our expression. And when we do that, we get 1 over the square root of e to the 2x times 1 minus e to the minus 2x. We can then go and split our square root apart, so our denominator then looks like a square root of e to the 2x times the square root of 1 minus e to the minus 2x. And when we take that square root of e to the 2x, we'll just get an e to the x. So now what I want to do is I want to get things into the form that we have from that derivative of arcsine. So to do that, we'll take u to be e to the minus x. And what we have very conveniently is that e to the minus x is sitting up in our numerator. So we have our, just because we have a 1 over e to the x in the entire expression. So same as e to the minus x in the numerator. So our du is going to be minus e to the minus x dx, or dx is minus e to the x du. Okay, so then we started with trying to find the antiderivative of 1 over e to the x times the square root of 1 minus e to the minus 2x dx. And after substituting in our expression for u, we get minus the integral of e to the minus x times e to the x, all divided by 1 minus u squared du. So our e to the minus x will cancel with the e to the x, and we'll just be left with an integral of 1 over 1 minus u squared du, with the minus sign out in front. And as we just said, that's the that is the derivative for arc sine. So that tells us that our antiderivative here is just going to be minus arc sine of u plus c, and we'll put back our original expression for u. So in the end, the final answer is going to be minus arc sine of e to the minus x plus c. So the last example that we have here is going to be slightly different, because what we see is that we're going to find an integral between 0 and pi. So we're going to find the net area for some function in between 0 and pi. So the previous 6 integrals, we haven't had any examples like this, so we just wanted to see one example of how things change when we have bounds on the integral. Okay, so the first thing that we're going to do is we're going to want to make our substitution as regular. So we're going to take u to be 2 plus sine of x over 2, and that way a constant multiple of the derivative, in this case 1/2 cosine x over 2, is going to be sitting in our numerator, because we see that we have a cosine of x over 2 that's in the numerator as well. Okay, so then doing this, we're going to have that dx is going to be 2 divided by cosine of x over 2 du, and then we're going to go and put that expression into our integral. So we'll get the integrand will now be u squared cosine of x over 2 times 2 divided by cosine of x over 2. So the cosine of x over 2's will cancel each other out. Now the interesting part here is these bounds. Because what we're doing is we're changing everything from looking at things in terms of x to looking at them in terms of u. So the bounds that we have, 0 and pi, those are defined in terms of x, so we just need to ask what are the corresponding u values. So what we're going to do is we also need to go and substitute the bounds that we have into our expression for u. So what this means is evaluate u at the lower bound of 0, and whatever we get there will be our new lower bound. And then also evaluate u at the upper bound pi, and whatever we get there will be our new upper bound. So when we go and we evaluate u at 0, we get 2 plus sine of 0, which is 2, and we evaluate u at pi, we get 2 plus sine of pi over 2, which is going to be 3. So this tells us that our new integral is going to be finding 2 times the integral from 2 to 3 of u squared du. We do that quite easily. We get 2/3 u cubed evaluated at 2 and 3. And when we evaluate that integral, we get 18 minus 16 over 3, which is 38/3. Okay, so pictorially what we've done is we've taken this gray region, so this is the function 2 plus sine of x over 2 all squared times cosine of x over 2 between 0 and pi, and what we're going to do is just transition this into u space. So we have the bottom axis is in x space, and the y-axis is f of x. Here's giving us the corresponding f of x values. We're going to transition this into u and f of u space. And when we do that, we just get this nice parabola, which is much easier to go and find the area of. Okay, so that goes and gives us everything we need to do to go and undo the chain rule. And this should serve you well whenever you go off to Calc 2. So this gives kind of an introduction to half of the main techniques that you use in Calc 2, and the next video I'll go and wrap up with undoing the product rule, which is kind of the other main technique you use in Calc 2. Alright, so I will see you then.